Okay, so yeah, that's actually a fairly interesting observation. So if you're jumping around and you see that if you jump in here, it's always a problem. Either that's faded out or it's always interfered with. And you might even be sophisticated enough to identify which of those two problems is happening. In principle, you could rearrange your radio to always avoid that band. That's
That might take more performance anyway.
that's true. However, that's actually a very hot area of research right now. It's called the cognitive radio. So what would happen? Basically, you would start out looking at your entire frequency bandwidth. You would try to identify who's out there and who's transmitting. And in fact, you could do this in both frequency and time. You could identify who's using which frequencies and particularly when they're using them. So if there's a guy who's using these bands at this time, and then always 5 seconds later he uses them again or something, you could learn that and avoid them. So that's actually, there's a lot of research out there on that right now.
There's a guy that does that kind of research.
Correct.
They actually do TLS.
Correct. There's actually, there's lots of people all over the world doing work on it. So. Okay. So why do this? Why frequency hop? So what you can do is you can avoid fading. You can avoid interference. And you can avoid other Bluetooth users. And all these are at the expense of occasionally losing slots. So you always have to, you have to have, these don't, frequency hopping is not a magical recipe for always avoiding these problems. What's going to happen is that when you encounter that problem, you quickly run away from it, but you'll probably come back to that problem again later. So you have to deal with the packet losses that you're going to incur. Similarly, okay, frequency hopping spread spectrum is just one kind of spread spectrum. Who can tell me another example of one? Spread spectrum. CDMA, perfect. So what happens in CDMA? Basically, we spread. We use a spreading code to spread our signal all over the frequency bandwidth, and the trade-off for that is that we have to be able to put up with other users who are also using CDMA who are interfering with us. So philosophically, it's the same kind of idea. Okay.
But does the characterize have to know what
Pardon me?
frequency you're on right now?
Yes. So
I don't think it's random.
it's pseudo-random. In other words, it's like a random number generator loaded with a particular seed. So it's not strictly random, right? But it is pseudo-random.
Would Aloha count it the same way for time, since it's a random backoff? If you're randomly trying to filter the channel,
It's a good question. I don't know. Could
it's
you
a little less elegant, maybe.
Maybe. So I think the key idea here is there's sort of a frequency and time component, and similarly with CDMA, I mean it's you're spreading your signal all over frequency and time, but I don't necessarily see how that would fit in with Aloha. But that's an interesting observation. Yeah, that's cool. Interesting. Okay. So, as to address Adrian's point, when a piconet is formed, the master sets the hop sequence. And it does that based on its own unique device ID. So in other words, the master, I said every device can act as either the slave or the master. If a device is acting as the master, it has its own unique device ID which specifies its spreading sequence. So in other words, a device acting as the master always uses the same spreading, always uses the same hopping sequence. What's more, so we have the star topology, and we always use the same, we need duplexing because the slaves need to communicate with the master and vice versa. The type of duplexing we use is time division duplexing. And in particular, the order of transmission is basically this. It's always master followed by one of the slaves, followed by master, followed by another one of the slaves, and so on. So it's always master, let's say slave 1, master, slave 2, and so on, up to master, slave 7, master, slave 1, and so on, like that. There's an exception to this, and that is when it is possible for transmissions. So these are by slot. So slot 1, master, slot 2, slave 1, slot 3, master, and so on. So in other words, these would be each individual discrete frequency hops. So you'd hop into the diagram I had up a second ago. Each block, one of those blocks would be this, the master's transmission. The next block in time would be slave 1. The next block in time would be master, and so on. The exception to this is that it is possible for transmissions to occupy more than one slot. Here's what that would look like. Basically, they just go on in time. So let's call this figure 4. So the one slot method, one slot at a time, every 625 microseconds. For instance, we have master, slave 1, master, slave 2, master, and so on with a bit of a guard time between them. And I don't want to draw this jumping around frequency. I'll just write the frequency up here. So it'll be frequency 1, frequency 2, frequency 3, frequency 4, frequency 5, and so on. So it's possible for transmissions to occupy, let's say, 3 slots. It's possible for them to occupy 3 or 5 slots. How that would work, let's say the master transmits, and then this slave suddenly decides I have enough information that I want to occupy 3 slots. So that's negotiated by some protocol mechanism. So you would have a continuous transmission of slave 1 through those 3 slots. This happens at frequency 1. Slave 1 then stays at frequency 2 for this entire transmission. And then we come back to master at frequency 5, not frequency 3. So basically we sort of, this occupies, this sort of stands on top of all of this, and then we come back to where we left off. The reason for that is to make sure that everyone's synchronized. If we didn't do this and somebody missed the control message, over here, some devices might be on frequency 3 and others might be on frequency 5. So just to make sure that everyone's hopping in lockstep. There's always sort of everyone's always on the same page. And if someone is transmitting, they won't want to change frequency. So just stay at frequency 2, skip over 3 and 4, and then come back to 5.